Got it. So I can handle that. And Jeff, you want to start the introduction?
I'll go ahead and start.
Should we get
Hello.
started?
Yep. Hello, everyone. You all hear me? Hello.
I can.
Okay. Good. All right. So I'd like to welcome everybody. Today's webinar is on climate change and sponsored by Ground Loop Design Software. This is the seventh in a series of monthly presentations that we've been doing for geothermal design professionals. And if you want to go back and revisit this or any of our other previous presentations, please visit the Ground Loop Design website. It's www.groundloopdesign.com. Click on the webinars choice, and it will allow you to go back and do any of our past webinars. And I said this is our seventh one so far in the series. So today's presentation is going to be given by Dr. Matthew Schmidt. And Dr. Schmidt has a PhD in geology from the University of California, Davis, and is currently an associate professor in the Department of Oceanography at Texas A&M University. Dr. Schmidt's received honors and grants from the National Science Foundation for his work on climate change. And there's a lot of stuff I could read, but I think at this point I'm going to pass the meeting over to Dr. Schmidt. Welcome.
Well, thank you. Thanks for inviting me. I need to find that button to share my presentation. Right?
Okay. Yeah. So basically, you need to find the share screen. So you see at the top of your screen there may be a quick start. There may be a couple tabs. One says quick start or meeting info. Go to the quick start one, and then the share my desktop button should be there. There you go.
Got it.
Right.
Can you see my desktop now?
Yep, I can see it. Looks very clear.
Great. Okay, so my presentation's up?
Yes, you're good to go.
All right. Well, thanks, everyone, for signing in to hear a little bit about my research and my background. And then I'm going to talk about climate change and where we're going in the next century and why there's such an important need for green design in our future. So just a little bit of the first quarter of the talk, I'm probably just going to talk about my background and what I do. It's maybe unrelated, but that's a little curious. Basically, I'm a geological oceanographer, which means that I'm a geologist by training, but I work in the ocean. And my research focuses on using marine microfossils to reconstruct Earth's climate history. So they call me a paleoceanographer, a paleoclimatologist. And the primary tools that I use are ocean sediments and tiny creatures that are preserved in the ocean sediments. So first of all, what I'm showing you here is just, probably you're familiar, I don't know if you've done any seismic work, but this is just a seismic profile of a sedimentary layer from the bottom of the seafloor. And you can see these nice laminated horizontal sediment layers which each record a snapshot of Earth's history, climate history in the past. And so our goal is, the way we do our work is we go out and we collect cores, we penetrate these thick sequences of sediments, retrieve cores, and then study the details of sedimentation, the chemistry of those layers to tell us about past climate change. And so it turns out that ocean sediments are one of the important archives of Earth's climate history. We can generate records that go back millions of years in the past that understand long-term as well as rough climate history of our planet. It tells us things about past temperature changes on our planet, how the ocean and the atmosphere make circulation patterns were different in the past. And all of this comes about, like I said, from retrieving these small sediments. I'm showing you here a picture of me and some of my students. We're out on a cruise in the eastern Equatorial Pacific, and this is a freshly recovered core that we just split open. You can see this ash layer, this dark ash layer, which we know dated to 84,000 years ago. It gives us a nice timeline, a nice chronostratic time point for our records. So next, I just want to give you an overview of how we actually go about collecting these sediment cores. There's basically two main ways. One of them is a very successful program called the Ocean Healing Program. It's been around for many decades, sponsored by the National Science Foundation. and they basically operate this ship, which is a mobile drilling platform. And they can go anywhere in the world's oceans, and via this drilling platform can recover very, very long sediment cores, marine sediments, and it can actually also drill into the crust of the ocean and bring back samples from the actual bedrock of the ocean floor. Another way that we do it, if you're only really interested in the upper layers, is to collect what's called piston cores. And so this is a piston core that's being deployed. It's basically just a large core on a large lead weight shoved down into the sediment. And we can get cores. This is a core that we brought back to our ship that are on the order of 20, 40, or maybe 60 meters long. And so you can imagine all the layers of mud in here that record changes in climate history. The next step, what we do is we split the cores in half. And so this is just an illustration on the upper left of those cores that have been split open. And you can see all the different color changes as you move down through the core. And these all represent changes in the chemistry and the climate of those paths. But what we do in particular is we first sample the core, like say every 5 centimeters or every 2 centimeters. We bring it back into the lab, and the first step is to wash away the mud, which is what my undergraduate student Amy in the middle here is doing. And then we wash it over a sieve, very low tech, and just collect the coarse fraction. And what's left in the coarse fraction is almost entirely foreign manipulative shells. And I'm going to show you what those look like next. This is my grad student, Bill, a few years ago, who then sits at a microscope and picks individual species of planktonic manipulative. So I want to introduce here what forams are. If you've never heard of these little creatures, these are blow-ups of what they look like. They're actually the size of the head of a pin. Imagine a tiny little grain of sand, but it's actually a shell that's made by a protozoan, a single-cell protozoan that secretes this multi-chambered cell. And when these are pictures of living forams, they have spines that radiate from the central shell when they're alive. And they live throughout the world's oceans, and they record clues about Earth's history, the temperature of the water, the salinity of the water, the pH, and so forth. And then divers, research scientists, will go out, they collect these living forams, they bring them into the lab, and then they can calibrate the chemistry of their shells with many, many different parameters in the ocean water. And in particular, what we're interested in is temperature, salinity is mainly what I work on. So anyway, this is what they look like in life. When we get them in the marine record and the fossil record, after we wash away the mud, like I showed you, this is primarily what it looks like after you wash the mud away. We have the coarse fractions almost entirely tiny little individual foran shells that are made up of calcium carbonate, same as like a seashell. So you can get an idea of all the different species that are present in just one core site. And the amazing thing about these little guys, like I said, they're like about the size of a pinhead, one individual shell, is that they live throughout the oceans, and there's certain ones that only like to live in the tropics, others that live in the subtropics, and some in the polar regions. So just looking at the faunal abundance in these sediment cores, that's one way to actually reconstruct Earth's climate history. But another way, the way that I like to do it, is to use the chemistry of the shell to give us a more quantifiable value on past, let's say, temperature changes. And so what I do, you can take that shell, the species that I like to use, I have pictures here, it's called Globigerinoides gruber, and it lives in the upper water column. You can take their shell and you can dissolve it in acid and make carbon dioxide that we can then measure on a mass spectrometer and measure what's called the stable oxygen isotopic composition of that calcite, that original calcite. And so it sounds complicated, but it's really just a ratio of isotope of oxygen, O18, relative to the normal isotope of oxygen, O16. And it turns out that very subtle differences in that ratio, which we call delta, tell us about temperature, tell us about changes in temperature. So we can actually calculate a temperature at which this guy lived by measuring this value on mass spectrometer. Another thing that we can do is measure the trace metals in the shell. So it turns out that some of the calcium can be substituted for by magnesium. And this actually happens, again, it's a temperature-dependent reaction, so we can ratio the magnesium to calcium in the shell, and thanks to those calibrations that researchers have done on living forams to determine what the temperature was when that got lit. So, for instance, we can, well, first, I just want to show you real quick, this is the instrument, this is a picture of one type of instrument that we use. It's called a inductively coupled plasma mass spectrometer. And this is the instrument that we use to measure the trace metals, the magnesium, calcium, those temperature records. But when we have those, let's say at one spot, let's say at 1 sediment core in one spot, we can combine the data through many, many researchers' efforts to get a global picture of what climate was in the past. So what I'm showing you here is just an example of how we can use the data that I generated from my research to create a picture of what the Earth's climate was like, say, 20,000 years ago when we were in what's called the last glacial maximum. And so this is the time period where the ice sheets on North America, Europe were at the maximum extent. Climate was at its coldest period over the last 100,000 years. And so this is kind of like a benchmark of like the coldest period over the last 100,000 years. So climate scientists are really curious to know how the Earth's climate system works. And so by using the tools I showed you, you can piece together the individual data and create a model of how the Earth cooled at 20,000 years ago, what the global temperature gradients were like during the last ice age. And it's quite an amazing picture, really. You can see that the northern hemisphere cooled much, much more on the order of 10 to 7 degrees Celsius relative to modern, relative to the tropics, which didn't cool very much, and relative to the southern hemisphere, which cooled even less for the most part. So you can see it's not an even amount of cooling. You can get a global distribution of what the surface temperature gradients look like in different parts of our planet. So anyway, that's just a background of what I do. Then I want to talk now, I'm going to switch gears and talk more about where we might be going in the future, how we can use this information in the past to try to predict where we're going in the future. And so we can turn our model, the same type of models that generated this image of the climate of the past, and we can look toward the future. So I'm just going to briefly introduce what the greenhouse effect is and why this is really the major factor that's coming into play for how models are going to predict where we're going in the future. So basically, greenhouse effect works just like a normal greenhouse. It allows it allows visible light from the sun to come into hit the Earth's surface, but then because CO2 likes to absorb heat radiation, it prevents the heat that's generated from radiating back into space and warms the planet. And so it basically looks like this if you look at electromagnetic radiation. Incoming light from the sun is in the visible range, a shorter wavelength. That hits the Earth warms at the surface, and then re-radiates infrared or heat radiation, which is then trapped by the CO2 in Earth's lower atmosphere. Now, the greenhouse effect is not all bad, right? We actually are glad Earth has a natural greenhouse effect because it keeps the lower part of the atmosphere, the troposphere, warmer than it would be if we didn't have it. So it turns out that if we didn't have, so what you're looking at here is just a temperature profile through the Earth's atmosphere. And we live down here in the troposphere where the weather all takes place in the lower 12 kilometers of the atmosphere. And so you can see it's unique. The temperature basically drops in the atmosphere until you get to the troposphere, and then it starts to rise toward the surface. And this rise in temperature toward the surface is largely controlled by greenhouse gas effect. So if we didn't have the greenhouse gases warming the planet, keeping the heat that's generated down here from escape into space, our global temperature would be on the order of like negative 18 degrees Celsius instead of where we are today, a nice comfortable 15 to 20 degrees Celsius. And so by adding more CO2, what we're effectively doing is we're just going to increase this how the lower troposphere is warm from the bottom up, and we'll end up with a future that's somewhere like this slope, the green slope, with warmer temperatures in the lower troposphere. Okay, so the problem here is as I just illustrated, is that we're adding more CO2 to the atmosphere through the burning of fossil fuels, right? And we can measure that. In fact, we have been measuring that directly out in Hawaii, out of the volcanoes in Hawaii. They've actually been taking direct measurements of CO2 in the atmosphere since about 1956 or 1957. And so you can see that there's been this basically exponential rise in CO2 across the second half of the 20th century that's directly related to the burning input of CO2 in the burning of fossil fuels. And so if we look at where that's coming from, where the majority of that CO2 is coming from, it turns out it's not transportation and automobiles, but it's actually electricity. So I thought this is relevant to what you guys do, since the efforts that your company is doing will help cut down on the need for electricity from fossil fuels. And so this is actually, like I said, the biggest contributor to CO2 emissions over the last half of the 20th century in the future. The other thing I want to point out on here is that the lifetime of CO2 in the atmosphere is quite long. It's on the order of centuries, a couple of centuries. And so all the CO2 that we've been adding over the last 100 years, most of it's still in the atmosphere and will remain there for another century. So the net effect is really cumulative. So we're just really compounding our problems as we move toward the future because of this lifespan. Okay, so the question, of course, becomes how critical is it? How important is it? I mean, how can we measure? How unusual is it to have this amount of CO2 in the atmosphere? How can we go back farther than the direct measurements to see if it's really unusual to have this much CO2 in our atmosphere? And so the one way that we can do this as climate scientists, instead of using marine sediment cores, it's just another archive of the actual ice cores collected from cores in Greenland, Antarctica, and actually even they've basically been scientists have been collecting ice cores from all around the planet, even in the low latitudes, in the mountain regions, where there's mountain glaciers. All of these cores are being used to archive this climate history as a second archive relic, so we can compare to the marine record. So you can actually see in the ice cores that they're deposited layer by layer, year by year. You can see some of the layering in the lower core. And then if you look really closely and shade the ice cores very, very thinly, you see tiny little bubbles. It's like a very thin section of the ice core with these little bubbles. And it turns out those bubbles trap a little bit of Earth's atmosphere at the time of formation. And so scientists have actually analyzed those bubbles and analyzed how much CO2 is in those bubbles. And this paints, I think, a really clear picture of how unusual this rise in CO2 is in Earth's climate system. So on this slide, what I'm showing you, these are years that hit 2000, year 1800, back to the year 1000. And so what I'm showing you on this slide, this is from the IPCC report, which I'm going to talk about next. But this is the period of direct measurements right here, where we've actually been measuring the CO2 rise in Earth's atmosphere. And this is what the ice cores tell us the CO2 has been doing over the last 1,000 years. So I think by looking at this picture, you get a very clear image that it really isn't until the mid-1800s, when the Industrial Revolution starts, that the CO2 levels start to rise, and then they really ramp up across the 20th century, and then they're going to continue. These are the projections of the model of where CO2 levels are going to be in the near future of the next century. So it really is clear that man is having a big effect on CO2 levels. Now, can we go back even farther than 1,000 years? The answer is yes. The ice cores actually go back about 700,000 years, some of the ones from Antarctica. So, but on this slide, what I'm just showing you the CO2 levels in Earth's atmosphere back to about, here's time starting with today. It's 100,000 years ago, 200, 300,000 years ago. So in total, it's basically 350,000 years of history. And then what you're seeing here is 3 glacial cycles. You've got one glacial cycle here, a second glacial cycle here, and a third glacial cycle back here. And so in blue is the CO2 trapped in the ice bubbles from Antarctica. going back in time. And then in red, and corresponding to the left axis, is temperature in that same ice core. So in red, it's the temperature measured in the ice core, which I'm not going to explain how we do that. It gives influence on the oxygen isotopes, but we have a pretty clear understanding of how the ice core can tell us about temperature. And so what should stand out here, and it's so remarkable, I think, in my mind, is just how tightly coupled the CO2 is to the temperature over 3 glacial cycles. And when it was warm in Antarctica, in these periods, CO2 is around 280 parts per million of concentration in the atmosphere. And when it was cold, remember I said the last glacial maximum is the coldest temperature of the last glacial cycle. That's about right here. So each glacial maximum, going back 3 glacial cycles, the CO2 always comes back down to about 180 parts per million. And so what I want to point out here is that it looks like to go from a full glacial state to a full interglacial state, it's really only about 100 parts per million CO2 variability. And so clearly there's something critically important about CO2 levels and temperature in this climate system if you base just on this relationship. And so finally what I want to show is what we've added to the where we are today, where the CO2 levels are today. This is what's so shocking and I think alarming as a climate scientist. We're up here, we actually passed, hopefully some of you saw this on the news, back in May of this year, we actually went above 400 ppm of CO2 for the first time. And so this was a big benchmark, and we're above it, we're already above that level today. And so clearly, as long as the ice core records exist, never been at this level, and they go back almost 1 million years. So we think we have to go back about 300 or about 3 million years before be able to reach a period of Earth's climate history where CO2 is at 400 ppm. So that's where we are today. We're climbing. It's going to be higher than that next year. And so the big question is, does adding CO2, this is where the debate comes in, does adding CO2 lead to global warming? So that's the big question. And to answer that, we have to use our climate models. We have to rely on big synthesis of data sets, and all of that's kind of brought together in what's called the Intergovernmental Panel on Climate Change, or the IPCC for short. And so hopefully you all are aware that the fifth assessment report, they've basically been doing these reports every 5 to 6 years since 1990. And so this is the fifth report. It's just coming out this year. They've released parts of it. It's a major effort put together by over 209 lead authors from 39 countries around the world. There's over 600 total contributing authors to this report on where we're going, where the climate is going over the next century. Over 50,000 scientists have contributed some parts to it, and it represents 6 years of scientific work. So it's a really important document to understand where we might be heading over the next century. So what does the IPCC report conclude about anthropogenic global warming? That's the question I wanted to know. And so it's kind of interesting for a historical perspective to kind of look back over the 5 reports to see how the language has changed since 1990 about man's influence on climate change. And so if you go back to the very first report in 1990, they expressed some concern that there could be some of the warming over the second half of the 20th century could be man-made. But the key is they really couldn't discern whether that was natural climatability or man-caused, so or man-made. So they really didn't know as recently as 1990. Then 5 years later, if you look at the second assessment report, there's a little more evidence. They're starting to say, oh, the evidence is starting to suggest there is a human influence, but they weren't really ready to stick their neck out and make a big claim at that point. 2001, finally, they say that there's stronger and new evidence that human activities are doing it. They're starting to get better handles on the natural variability and be able to say that some of the warming is caused by man's influence. Then in the fourth report in 2007, their language got stronger. They're saying that it's very likely that many of the observed trends in warming since the mid-20th century are due to anthropogenic greenhouse gas concentrations rising over that same time period. And then finally, the last report that's just coming out this year finally gets to the point where they're ready to say it's extremely likely that human influence has been the dominant cause of observed warming over this time period. So I think, these are really the experts in the field, and if they're willing to make such a strong statement, I think we have to put a lot of weight on it and be aware, be concerned. And I think society needs to be concerned that this really is going to be a problem over the next century. Okay, so what have we achieved so far? Where have we come so far? How much warming has the Earth observed? So this is hot off the presses from the working group. From the IPCC report, annual assessment report number 5. It shows the actual warming that's taken place around the planet up to 2012. So you can see there is still an uneven distribution of warming. The largest warming, upwards of 2.5 degrees Celsius, is going to be in the interior of the continents. Oceans are probably warming a little bit slower, but overall you can definitely see that there's a warming trend visible taking place on our planet. And so the next question, of course, is where are we going by the end of the century? Where does this IPCC report say that we're heading by 2100? So in order to try to figure that out, what they do, it's a little bit complicated with these RCP scenarios. But basically they try to take different scenarios of where they think we're going to be as far as CO2 levels by the end of the 21st century. And so the lowest level, they say that would be we finally end up at 421 parts per million CO2. Now keep in mind, we're already at 400 in 2013, so I think it's highly unlikely that we're going to be 421 by the end of the century. So this case is probably too optimistic. This represents extreme mitigation starting now, and it's probably unlikely that society is willing to take those efforts. The more likely case is that we're going to be somewhere in the range of 538 to 670 by the end of the century. And then the worst case scenario would be business as usual, we do nothing, and nothing beyond what we're doing today, and we end up at this really high rate of 946 ppm. So either way, even the extreme mitigation case, this is the warming achieved by 2100. This is the worst case scenario, warming, a very warm world, where you're seeing warming upwards of 11 Celsius at a huge part of the planet. So again, I think this is probably an extreme. Hopefully we won't get there, but even in the best case, we're going to still see warming on the order of 1 to 1.5 degrees beyond what we've already experienced during the second half of the 20th century. Okay, so just to show you another way of looking at it, these are the different scenarios: extreme mitigation, the worst case, and then these are the more likely scenarios. And this would be the temperature change according to those scenarios. This would be the possible error associated with each model. So if we just draw a line here through the middle of what these likely scenarios say, it says that we're going to be looking at a world that's on the order of 2 degrees Celsius warmer, very likely by the end of the 20th century. Okay, so what are the consequences? Some people will say, so what? It's warmer, so be it. I like a warm climate. Well, there's a lot of consequences, right, to a warmer climate. And one of the most direct and obvious consequences is that we're going to start to raise global sea level as the warmer planet melts the ice sheets up on Greenland and Antarctica. It's also going to cause the global oceans to warm, and that's going to cause thermal expansion and additional sea level rise. So it's really critical to know where how much sea level rise we'll expect over the next century. And so if I draw a line here through the most likely scenarios, remember the middle two, and then take the errors associated with them, you're looking at a sea level rise on the order of, this is in meters now, so you have over 0.3 meters, upwards of 0.6 meters. So more than a half a meter of sea level rise, which is very significant. And in reality, probably it won't be even throughout the entire world. This is from also from the IPCC report. The sea level rise is actually vary from place to place on the planet. Some places will experience more sea level rise, like in a high latitude. Some places will experience less sea level rise just due to changes in ocean circulation patterns and some other parameters. So it's a very complicated thing to predict, but it's critical that we think about it because most of the world's population, of course, lives near the coast. So regardless, and this is going to displace millions of people worldwide, just very small changes in sea level rise. So it's something that's going to probably be one of the major impacts of a warmer planet. Another impact of increased greenhouse gas effects over the next century, and I put this in because I thought it was something that you guys might be interested in, is we're actually going to see an increase in the nighttime temperatures faster. That's basically the nighttime temperatures are going to increase faster than the daytime temperature increases. What that means is that there's going to be a smaller diurnal temperature range as we have more CO2 and greenhouse gases in the atmosphere. So these are just the models. This is actually observational. Excuse me. Over the 1950 to 2000, it shows how the nighttime temperature lows are rising faster than the daytime highs, and so that diurnal temperature range decreases. So this is going to be consistent with global warming, and so this is going to actually continue. This trend should continue into the 21st century. Might be something you need to consider with your energy balances in your systems for homes and businesses. Okay, another thing that's expected to change is the sea ice extent in the Arctic Ocean is expected to significantly decrease during the summertime. And in fact, the Arctic will probably be sea ice free by the end of the 21st century, at least in the summertime. And that's going to have a huge impact on warming the polar regions. So this is looking down North Pole. We're going to be, the northern hemisphere is going to experience even larger degree of warming than the sea ice is going. And for one thing, it decreases the albedo when you have an open ocean up there, which is going to amplify the warming warmer in the Arctic. And these are alarming trends that have been going on over the last several decades. What I'm showing you here is observational data since the sea ice decrease in the Arctic since they've been keeping records since about the 1970s. Yeah. And so what you see here in purple is where the normal, the median extent of the sea ice should be at the end of the summer in the Arctic region. And so it turns out that 2005, 2007, 2012 were all record-breaking low amounts of sea ice in the Arctic Ocean. The sea ice cover got smaller and smaller and smaller. In fact, in 2012 was the lowest recorded on history, lowest recorded since they had satellite data in the Arctic region. So this is alarming. A lot of climate scientists have seen this trend already happening. So I don't think it's unreasonable to think that another degree or two of global warming, this trend is going to get more and more extreme as we move into the future. Another thing that's going to happen in the U.S., North America, is the snow cover is going to get less and less. And so many models are predicting that the snow cover in most of the continental U.S. will decrease by 50 to 100%, which means no more snow, no more skiing in the Rocky Mountains in the second half of the 21st century. It's highly unlikely, so that's something else to consider. And then the final thing I want to talk about, what the CO2 is doing to our climate system. I don't know that a lot of people think about this, but not all the CO2 stays in the atmosphere. And so what I'm showing you on this bottom plot down here is the flux, the total flux of CO2, carbon that's given off through fossil fuel burning. And then this is the actual rise in the atmosphere in red. So the question is, where's some of this going? And it turns out that about 30% of the CO2 that's in the atmosphere that we put into the atmosphere manosphere, the atmosphere, has actually been absorbed by the global oceans. And so the oceans are acting as a sink. They're sucking up the CO2, and it's actually causing a change in the ocean pH. The chemistry of the oceans is actually changing. The oceans are becoming more acidic as they suck up the CO2 and make carbonic acid, which lowers the pH of the ocean. So we're just seeing, this is the PCO2 in the atmosphere on this plot. This is the pH of the ocean, and then it's modeled in the future to continue to drop. And as the pH drops, the carbonate ion and the bicarbonate is also going to drop in the ocean, and that's going to affect everything in the ocean that makes a shell out of calcium carbonate. So everything from the forams that I talked about before, coccolithophores, which are types of algae that make a calcium carbonate skeleton, to even the coral reefs. All the coral reefs make calcium carbonate skeletons. So all these things are going to be heavily impacted by ocean acidification, and in effect will not be able to build the skeletons and will most likely die because of that. So we're talking about huge mass extinction in the ocean as the pH drops due to the rising carbon dioxide levels. So those are just some of the things I wanted to talk about, where we're going in the future, what some of the consequences are. And then the other thing to keep in mind, not to be too depressing, but the really bad news I said here is that the CO2 is going to stay in the atmosphere for centuries. So even if we stop the CO2 or leveled it off at modern day levels, the warming is going to continue for many centuries to come. And so I just highlighted, these are some text out of the new report, that the warming in the models, we look beyond 2100, is expected to continue under all the scenarios, except that one that I showed you, that extreme mitigation, which is highly unlikely, the one that puts the CO2 levels at only 421 parts per million by the end of the century. So this is something that we're committing ourselves to, not just our generation, but many generations down the road. So I think that's something else that the public is aware of. And so just to kind of wrap it all up and end it, just wanted to show you this one article that appeared in Scientific American that's based on some of the research that these two professors at Princeton, at the Princeton Environmental Institute, the Carbon Mitigation Initiative, have been working on. And I thought I just wanted to talk to you guys about it because you're part of the green energy industry. But they came up with these ways, they called it wedging your way to a cleaner future, a CO2, reduced CO2 future. And so what they wanted to do is prevent Earth from experiencing a level of 560 parts per million CO2, which is essentially double, that's 2 times the pre-industrial level. Remember, the pre-industrial level in the ice cores was about 280, so this is double that value. And so if we look at our current, where we've been going over the last century, or the last 50 years, and we project that into the future, that same rise, we're actually going to achieve this 560, or 2 times CO2, pre-industrial CO2, by the year, right around the year 2050, 2056. And so there really is dire need we want to avoid that level, which most climate scientists agree is going to cause catastrophic change on our planet. We have to start thinking about ways of reducing that CO2 emissions today. And so they came up, I thought, with some clever ideas. Each of these, they call it a wedge. So it turns out we need 7 wedges to start to bring down the CO2 emissions and level it off so we don't reach that 560. And beyond that, we can talk about how you can actually bring it down, start to decrease CO2 in the atmosphere. So it is possible. The conservation and technology is going to involve hard choices. But I just wanted to show you, these were they basically came up with 15 doable, which they argue, and I think most of them are doable strategies of reducing CO2. So like I said, all you need to do is achieve 7 of these to reach a world where the CO2 emissions bring it down to 2050 to what it is today. And so a big part of the 7 wedges are over here in the orange category, the alternative energy sources, where most of you guys are making a difference. And so all of this is going to add up. We need lots of strategies, but all of it's going to add up to making a difference in the future. That's the main point I'm trying to make here. So with that, I will stop and take any questions, or try to take any questions that you guys might have. Some of this is not really my area of expertise, but I'm glad to do my best to answer anything you're wondering about.
If anyone has a question, feel free to unmute their microphone and just ask, or conversely, feel free to just chat your question in. Those are two options. While people are waiting, sort of genuine thoughts, Matthew, I'd like to thank you for your presentation. It was great, and I have a question for you.
Yeah.
And right now we can see your desktop, just so you know. So I'm gonna.
Uh-oh.
You
see how messy
you might want to hit the stop share. Well, actually, I'll take control again. That'll save you.
I'm looking for that window. I can't find it.
Yeah, I took care of it. You're safe now.
Okay.
You are safe. So I have a question. It's not a scientific question per se. It's more about a personal question about sort of you and your colleagues who do research on climate science and climate change related issues. So when you get together with a bunch of your friends, you know, drinking a beer, what do you guys talk about climate change?
Oh, we just get really depressed, and I don't know. The really frustrating thing is that climate scientists are doing such a terrible job, I think, at communicating this to the public. That so much of the public are so ignorant of these changes that I guess we sit around and we try to come up with ways or try to speculate on why we're doing such a bad job. I don't have an answer to that. I wish I knew, but I think that's what's most talked about, how we can do a better job at communicating. I mean, because to me, in my mind, it is a complicated topic, and some people in the media like to make it even more complicated, but I don't know, the cost of not doing anything, the risk of not doing anything, I think it's just too great, and people just don't realize that. So, I don't know. That's one thing about that climate change.
Got it. Okay, so Bob has a question. Bob, I'm going to unmute your microphone so you can just ask away. There you go, Bob. Feel free to ask.
Can you hear me?
Sorry, Bob. I just muted you again, so let's unmute. Oh, you did? Okay, sorry.
Okay, can you hear me now?
Yeah, loud and clear.
You got me?
Yep.
Okay. How receptive is our government on these projections?
You mean to the IPCC report? Is that what you're asking?
What's that?
You mean how much?
Well, I was wondering how receptive.
Yeah. Well, so far we've done nothing, right? Very little. So I would say not. I mean, not very receptive. I mean, the U.S. has not taken any leads. Is not, stepping forward to make any really headway toward tackling this issue. So I don't think our politicians, no one is willing to make any sacrifices at this point that I've seen. We need to push on this. I don't know.
Yeah, because, I mean, obviously, how much of the scientific, in this, the scientific community, how much of this are they kind of climbing on board with? I mean, is the majority of the scientific community in step with what you're talking about and what is actually happening?
I would say, yeah. I mean, yes. I think that the majority of the scientific community is in step or agrees with the findings of this report. I mean, like I said, this is a huge synthesis report. It's not just a few people working in a back room coming up with this report. These are the leading scientists in the field that are coming to these conclusions. So I would say only a very small percentage of climate scientists and academia would disagree, would come out and disagree with the findings of the IPCC report. There are some, but I would say it's like 95 to 5. 95% are in agreement, and maybe 5–10% would find fault with it or disagree. But they're on the fringe.
Okay. Thank you.
We just have to make the politicians. I don't know. We need to communicate to the politicians and get some action going.
Do we have any other questions?
Thank
It's a
you.
great opportunity. Sure, Bob, thanks. Any other questions? It's a great opportunity to ask someone who's a practitioner in the research field for his insights. No, doesn't look like there are. Well, we're gonna give everyone Dr. Schmidt some cell phone number so you can call him any time of day or night with your questions.
Yeah, but I keep in mind I'm more of a paleoclimatologist than a future climatologist. I can tell you anything you want to know about the glacial bowl.
So if I ask you, what was the weather like in 8000 BC?
Yeah, I can help you with that.
Got it. Well, well, if there are no further questions, I think we're going to call it a day. Thanks for everyone for joining. I think it's an interesting topic. Thanks for your efforts in the geothermal world, and a special thanks to Dr. Matthew Schmidt for spending some time with us.
Thank you for inviting me.
Thank you, Matt.
All right.
Thank you very much.
Thank you.